The 1940s were steam's last stand. Railroads bet everything on experimental locomotives promising to defeat diesel domination. What they got instead were mechanical nightmares that helped kill the very technology they were meant to save. The Atlantic Coastline R1 arrived in 1938 as Baldwin's grand proof that duplex power could actually work. It didn't. This ambitious 4444 was supposed to handle heavy passenger trains with smooth divided drive. Instead, it became a rolling lesson in why some ideas should stay permanently on drawing boards. The R1's fundamental problem was weight distribution. With two sets of driving wheels under a rigid frame, getting equal adhesion proved impossible. Front drivers would slip while rear drivers grabbed, or vice versa. Engineers spent more time fighting wheel slip than running trains. The backward-facing rear cylinders created maintenance nightmares. Mounted close to the firebox, they ran hot constantly and accumulated grit in every seal. Steam. Pipes ran so long that pressure dropped significantly before reaching cylinders. The ACL tested it barely 3 years before quietly returning it to Baldwin. The manufacturer's embarrassment was complete. They never spoke publicly about this locomotive again. But here's the thing. Despite this humiliating failure, Baldwin convinced Pennsylvania Railroad to try duplex power anyway. That decision would spawn even more spectacular disasters down the line. Pennsylvania Railroad's Q1 looked like the future when it emerged from Altoona Works in 1942. Streamlined by legendary designer Raymond Loewy, this imposing 4644 was supposed to prove duplex drive could handle heavy freight service. Instead, it proved some fundamental engineering mistakes refused to stay buried no matter how pretty the shell. The designers mounted rear cylinders backward, facing the firebox. This seemed clever on paper. It kept the locomotive shorter and balanced weight better. In reality, it created mechanical nightmares nobody anticipated. Firebox heat-baked cylinders constantly. Ash infiltrated every seal and bearing surface. Steam pipes stretched so far that pressure dropped dramatically before reaching pistons. Making matters worse, PRR gave the Q1 passenger-sized 77-inch driving wheels on a freight locomotive. Like putting racing tires on a dump truck. It struggled with heavy starts and couldn't develop proper tractive effort at low speeds. The firebox, constrained by backward cylinders, ran too small for sustained hauling. During its brief career, the Q1 accumulated just 165,000 service miles. Ordinary freight locomotives routinely passed 1 million. PRR redesigned everything for the Q2. They just didn't learn enough. The Baltimore and Ohio's George H. Emerson emerged in 1937 as America's first true duplex locomotive. Nobody at the railroad was particularly proud of it afterward. Built at B&O's Mount Clair shops, this experimental 4444 carried the name of the railroad's chief of motive power. Perhaps they should have waited to see if it actually worked before permanently attaching his name. The Emerson borrowed heavily from European experiments, featuring two sets of driving wheels under a rigid frame, each powered by its own cylinders. The theory was elegant. Smaller cylinders and lighter reciprocating parts would reduce hammer blow while producing smoother power delivery. In practice, the locomotive fought its crews constantly. Rear cylinders ran hot and wore out far too quickly. The dual throttle system required engineers to manually balance power between driver sets. Get it wrong, and one set slipped while the other overworked. Maintenance crews found critical components buried in hopelessly inaccessible locations. The B&O tested the Emerson for 6 years without ordering additional units. By 1943, it was quietly retired, having convinced management that duplex power was definitively someone else's problem. They chose diesel instead. When Baldwin pitched duplex power to Pennsylvania Railroad in the late 1930s, they promised a locomotive combining Pacific speed with northern pulling power. PRR engineering was skeptical, so Baldwin built the S1 to prove them wrong. At 140 feet long and weighing over 1 million pounds with tender, it was possibly the largest passenger steam locomotive ever built, and far too big to be useful. The S1's 6-4-4-6 arrangement looked revolutionary. Raymond Loewy's streamlining made it appear to be traveling at speed, even standing still. But beneath that gorgeous shell lurked fundamental flaws. The locomotive couldn't navigate most of PRR's network. Turntables couldn't handle it. Curves threatened derailment. PRR restricted it to just 283 miles between Chicago and Crestline. Wheel slip plagued every run. With driving wheels divided between two sets, achieving balanced adhesion proved impossible. At high speeds, the locomotive surged unpredictably as one driver set slipped and caught repeatedly. Engineers described fighting it like riding a mechanical bull. The S1 ran just 6 years before scrapping in 1949, teaching Baldwin nothing about why duplex designs kept failing. In 1944, Pennsylvania Railroad unveiled something that looked like a conventional steam locomotive but sounded different. The S2 steam turbine made no chuffing sound, just continuous whooshing as 6,900 horsepower drove wheels through a massive gearbox. It was supposed to combine steam's fuel economy with turbine smoothness. It achieved neither. The S2 represented the ultimate effort to make coal-fired steam competitive. Built by Baldwin and Westinghouse, it used a direct-drive turbine geared to driving axles. The gearbox transmitted power with 97% mechanical efficiency. But turbines have a fatal characteristic. They're incredibly inefficient at low speeds. Above 40 mph, the S2 performed magnificently, maintaining 100 mph while pulling heavy trains with fuel economy approaching diesel levels. Below 30 mph, it became a fuel-guzzling monster. Starting from rest, the boiler couldn't keep up with steam demand. Pressure plummeted from 310 psi to below 85. The firebox ran so hot at low speeds that staybolts cracked repeatedly. PRR stored the S2 by 1949. Turbines belong in power plants running at constant speed, not locomotives that must start, stop, and climb grades. The PRR's Q2 class represented everything learned from Q1's failure. Built between 1944 and 1945, these 4-4-6-4 freight duplexes were the most powerful, non-articulated steam locomotives ever constructed. They produced nearly 8,000 horsepower at Altoona's test plant. They could haul 125 cars at 50 menaxemes. And they consumed water like the ocean was running dry. The Q2 fixed backward cylinder problems by mounting all 4 cylinders ahead of wheels they drove. The firebox grew large enough for sustained hauling. An automatic wheel slip control system attempted to prevent violent slipping plaguing earlier duplexes. On paper, everything looked solved. In reality, new problems emerged. The slip control used electrical sensors and butterfly valves that proved unreliable. When working, the Q2 was magnificent. When failing, which happened often, the locomotive slipped violently at speed. High-speed slipping damaged drive gear and valve components. Boilers leaked chronically. Water consumption ran so high that Q2s required more frequent stops than conventional locomotives they replaced. By 1951, every Q2 was retired. PRR had no time to solve problems conventional steam didn't have. Pennsylvania Railroad's T1 duplex was supposed to kill diesel. When prototypes emerged in 1942, they looked like missiles. Raymond Loewy's streamlining created what many consider the most beautiful steam locomotive ever built. The 4-4-4-4 promised 6,000 horsepower with unprecedented smoothness. PRR ordered 50 production units before properly testing prototypes. This impatience would haunt them. Problems started immediately. Divided drive meant each driver set carried only half the locomotive's weight for adhesion. At starting, engines slipped violently. But here's where it got dangerous. They slipped at speed too. Imagine pulling heavy passengers at 80 mph when suddenly front drivers lose traction. The locomotive lurched, slipping drivers caught again, and the process repeated. Engineers called it dancing. Passengers called it terrifying. Franklin poppet valve gear proved equally problematic. More precise than traditional systems, it was far more complex. Components were buried where mechanics couldn't reach without major disassembly. When high-speed wheel slip damaged valve gear, repairs took weeks. By 1948, PRR announced all passenger trains would go diesel. T1s, some barely 2 years old, were scrapped. Oliver Bulleid believed steam could compete with diesel by making it vastly easier to operate. His SR Leader class, built between 1947 and 1951, was supposed to prove this revolutionary theory. What emerged from Brighton Works looked nothing like a steam locomotive. It looked like a diesel with a boiler hidden inside. Double-ended cabs meant no turntables needed. Enclosed running gear meant less maintenance. Every innovation promised efficiency. Every innovation failed spectacularly. The leader placed the fireman in a cramped compartment beside the offset boiler. During operation, this space became an absolute inferno. Temperatures exceeded human tolerance within minutes. Flames leapt into the cab when fire burned hot. Photos showed desperate crews running with doors open just to survive their shifts. Fire bricks collapsed repeatedly. Sleeve valves, which Bulleid insisted upon despite loud warnings, cracked constantly. One failure stranded the locomotive, requiring humiliating tows back to shops. During testing around Brighton, number 36001 broke down so frequently that crews lost count. Only one leader was completed. By 1951, British Railways scrapped them all, even partially built units, as if wanting no evidence this experiment ever happened. Chesapeake and Ohio Railway hauled more coal than any American railroad. Buying diesel fuel seemed like betrayal. When C&O needed passenger power for their proposed Chessie streamliner in the late 1940s, they demanded coal-burning locomotives. What they got were 3 M1 steam turbines representing the longest single-unit locomotives ever built, and possibly the most unreliable machines ever put on rails. Built by Baldwin and Westinghouse in 1947-1948, the M1 looked like nothing else on rails. Boiler sat at rear. Coal bunker rode up front, ahead of crew. Steam drove turbines powering generators feeding electricity to traction motors on every axle. A steam-electric hybrid designed to combine both worlds' best. It combined the worst instead. The M1 never made a single trip without breaking down. Every run ended with mechanical failures requiring shop attention. Coal dust from forward bunker blew back constantly, coating everything, shorting electrical systems. Turbines fouled with ash. Generators overheated. Traction motors failed repeatedly. The Chessie streamliner never ran revenue service. Neither did M1s really. After 3 frustrating years producing nothing but mounting repair bills, all 3 were scrapped by 1950. New York Central's Niagara class represented conventional steam's last gasp in America. Built between 1945 and 1946, these 27 484s were designed to run nearly 1,000 miles daily with minimal maintenance. Chief of Motive Power, Paul Kiefer, demanded they sustain 6,000 horsepower handling the demanding New York to Chicago corridor. They came heartbreakingly close to succeeding before metallurgy killed them. The Niagaras were magnificent performers. They routinely hit 100 met Tierman with heavy trains. Men in heat-resistant suits entered still steaming fireboxes to clean tubes, allowing locomotives to run 6 days weekly. This intensive maintenance demonstrated what steam could achieve when properly supported. But firebox wrappers cracked repeatedly. High-pressure operation exceeded what 1940s metallurgy could reliably handle. When Central tested Niagaras against diesels, results were close. Too close for diesel salesmen's comfort. But steam required heroic maintenance effort. Diesels just ran. Coal miners' strikes didn't help the cause. Neither did aggressive electromotive marketing. By 1956, the last Niagara was retired. None were preserved, a decision haunting railroad historians to this day. General Electric spent $2,1938 building the future of railroad motive power. What emerged were two sleek steam turbine electric locomotives designed to compete with diesel streamliners on Union Pacific's prestigious passenger runs. They looked like diesels, but ran on steam. They promised 125 mph speeds and double the thermal efficiency of conventional steam. They delivered 6 months of embarrassment. The GE steam turbines were engineering marvels on paper. Oil-fired boilers fed turbines that spun generators powering electric traction motors. Condensers recovered steam for reuse. Automatic controls managed complex systems. At speed, they performed brilliantly, accelerating faster than any steam locomotive UP owned. But railroads aren't racetracks. The turbines proved hopelessly unreliable in daily service. Boiler priming sent water droplets into delicate turbine blades. Feedwater pumps failed constantly. Condensers clogged. On one memorable occasion, both units failed while hauling a train from Colorado. A conventional Pacific steam locomotive had to rescue the rescuers. UP returned them to GE in June 1939. The project died by December 1941, replaced by big boys that actually worked. Britain's LMS Turbo motive emerged in 1935 as William Stanier's bold experiment in turbine propulsion. Unlike American attempts, this one actually worked. For 14 years, it hauled express trains between London and Liverpool, running smoother and burning less coal than its piston-powered sisters. Then, everything went wrong. The forward turbine's 18 rows of precision blading delivered 2,400 horsepower at 7,000 RPM. No hammer blow damaged the track. No reciprocating parts wore out. Crews loved its eerily smooth acceleration. But steam turbines have an Achilles heel. They spin in only one direction. The turbomotive's tiny reverse turbine had barely enough power to move the locomotive alone. Any actual reversing required stopping completely. Try that in busy terminal operations. By 1949, the main turbine failed, and post-war austerity made repairs uneconomical. British Railways rebuilt it as conventional Pacific number 46202 Princess Anne in 1952. Weeks later, it was destroyed in the horrific Harrow and Wealdstone disaster, killing 112 people. The turbomotive's story ended in tragedy. Only its boiler survived, salvaged and reused. Steam turbines never returned to British rails. Baldwin's Blue Goose looked like nothing else on American rails in 1950. Painted light blue and grey with orange stripes, this experimental steam turbine resembled a stretched diesel more than any steam locomotive. Twin turbines produced 4,000 horsepower, while the carbody could slide transversely over its trucks, providing an exceptionally smooth ride at its designed 100 mph speeds. Baldwin and Westinghouse built it as their last desperate attempt to save steam from diesel domination. They tested it everywhere. Pittsburgh and Lake Erie Railroad, Pennsylvania Railroad, Missouri, Kansas, Texas, Chicago and Northwestern. The Blue Goose outperformed pairs of EMD E7 diesels in comparative tests. It could do everything diesels did while burning cheaper fuel. Nobody wanted it. The problem wasn't performance, it was timing. By 1950, railroads had committed to dieselization. Maintenance departments were retraining for diesel technology. New shop facilities were being built for diesel repairs. Nobody wanted to invest in steam infrastructure for one experimental locomotive. Westinghouse couldn't find a single buyer despite successful demonstrations. The Blue Goose returned to Pittsburgh in 1953 and was quietly scrapped. The Erie Railroad's Triplex seemed like genius on paper. Why have one engine when you could have three? Built between 1914 and 1916, these two 8-8-8-2 monsters mounted 3 sets of driving wheels, including one set under the tender. 24 powered wheels clawed at the rails, generating 160,000 pounds of starting tractive effort, enough to snap couplers like twigs, enough to rip yard tracks apart. Getting that power moving proved the easy part. The single boiler couldn't possibly supply 3 engines at anything above walking speed. Test data showed performance collapsing above 15 mph as the massive cylinders literally starved for steam. Pressure would drop catastrophically whenever the engineer opened the throttle wide. The rear engine under the tender created additional nightmares. As water and coal were consumed, weight distribution changed constantly. The tender-mounted engine would slip differently than front engines throughout every trip. Yard workers nicknamed them yard rippers because that's what they did best. They could drag mountains of coal cars from terminals. They just couldn't get them anywhere useful. All were retired by 1929, teaching everyone that more engines don't mean more power. The LNER W1 emerged from Darlington Works in 1929, looking more submarine than locomotive. Beneath its smooth, streamlined shell lurked British Railway's boldest experiment. A water tube boiler operating at 450 pounds per square inch, nearly triple normal pressure, borrowed directly from warship technology. They called it Hush Hush, because everything about the project was shrouded in secrecy. Engineers were sworn to silence. Press was kept at bay. LNER wanted no publicity until they could prove high-pressure steam would revolutionize rail transport. Reality proved less cooperative. The water tube boiler demanded constant attention. Scaling and foaming clogged delicate tubes. Steam quality varied wildly. Pressure fluctuations could trigger cascading failures throughout the system. Maintenance crews dreaded every inspection. One missed deposit could disable the entire locomotive. The W1 spent more time in shops than on main lines. When it did run, performance never matched promises. LNER eventually rebuilt it with a conventional boiler in 1937, abandoning the high-pressure experiment entirely. The streamlined casing remained, hiding the failure underneath. Sometimes the most beautiful locomotives conceal the ugliest engineering compromises. Pennsylvania Railroad's V1 Triplex never turned a wheel because even PRR's legendary engineers knew when to quit. Designed in the mid-1940s as the ultimate coal-burning passenger locomotive, this monster would have combined 3 steam turbines with Raymond Loewy's streamlining and a modified Q2 boiler turned backward. At over 160 feet long, it would have dwarfed everything on American rails. The V1 existed only on paper, but those papers told a terrifying story. 3 turbines meant tripling everything that went wrong with single turbine S2. The backward boiler arrangement copied from C&O's M1 meant coal dust problems were guaranteed. Weight estimates suggested it would destroy track and bridges designed for conventional power. The S2's dismal performance killed the project before construction began. PRR engineers calculated that turbine fuel consumption at low speeds would bankrupt the railroad. Water consumption projections were equally horrifying. Sometimes the smartest engineering decision is knowing when not to build something. The V1 drawings went into archives, emerging decades later to show how close American railroads came to building the most spectacular failure ever conceived. Steam's death came before it could be born. Union Pacific's coal turbine number 80 represented the strangest marriage in locomotive history. Take a gas turbine locomotive cab, mate it with a Great Northern electric locomotive chassis, add a modified turbine burning pulverized coal, and somehow expect it to work. Built in 1962, this Frankenstein's monster combined the worst characteristics of every technology it attempted to merge. The concept made theoretical sense. Coal was cheaper than oil. Gas turbines could burn anything combustible. Why not grind coal to powder and blow it into the flame? Because coal dust contains abrasive particles that destroy turbine blades with terrifying speed. Every grain of unburned coal became a tiny bullet ricocheting through precision machinery. The grinding equipment itself caused endless problems. Too coarse, and particles damaged blades immediately. Too fine, and the grinding system consumed more power than it saved. Ash fouled everything. Filters clogged constantly. After just 20 months and fewer than 10,000 miles, UP gave up. The conventional gas turbines each ran over 1 million miles. Number 80 proved that some fuel sources should stay in the ground where they belong. Southern Pacific's cab-forward locomotives weren't failures. They were brilliant solutions to a specific problem. But the AC-12 class, built in 1944, represented the final evolution of a design that couldn't survive the diesel age. These 488-2 articulated locomotives ran backward, with crews riding ahead of the boiler, breathing clean air through Sierra Nevada snowsheds that would have suffocated them in conventional engines. Oil firing made the backward arrangement possible. Fuel piped from rear tenders to front-mounted fireboxes. No coal shoveling required. Crews loved them. Wartime records show AC-12s hauling 7,000-ton trains over Donner Pass with remarkable reliability. They weren't strange because they failed. They were strange because their very success highlighted steam's limitations. Despite working perfectly, they required enormous maintenance infrastructure. Each locomotive needed specialized facilities that diesels didn't require. When SP calculated total operating costs, including roundhouses, water stations, and specialized crews, the numbers told an unavoidable story. The last AC-12 ran in 1956. No amount of engineering brilliance could overcome basic economics. Sometimes the best steam locomotives prove only that steam itself was doomed. General Electric's 1938 steam turbines for Union Pacific failed after 6 months. Pennsylvania Railroad's S2 lasted 5 years. Chesapeake and Ohio's M1s survived 3. But Norfolk and Western's John Henry, named after the legendary steel-driving man who raced a machine and died, would outlast them all. It still failed spectacularly. Built in 1954, the John Henry was the longest steam locomotive ever constructed at 161 feet. It used a Babcock and Wilcox water tube boiler with automatic controls feeding turbines that powered electric traction motors. Starting tractive effort reached 175,000 pounds. On paper, it outperformed everything N&W owned. Reality proved different. The feedwater pump had to operate beyond design specifications, running to failure repeatedly. Coal dust infiltrated electrical systems despite every precaution. Automatic boiler controls proved temperamental. At speeds below 40 mmHg, fuel consumption exceeded conventional steam. Complex controls took engineers weeks to master. The locomotive was so long, it wouldn't fit on any N&W turntable. 3 years of testing produced only repair bills. N&W, the last major holdout against dieselization, finally surrendered. They ordered GP9s in 1955 and scrapped the John Henry by 1958.
Was radical. 8 driving wheels instead of 6 gave the P2 the tractive effort to haul 550-ton trains, upgrades that left other engines gasping. Only 6 P2 locomotives were ever built, making them among the rare express passenger locomotives in British history. The lead engine, Cock of the North, featured experimental marine-type poppet valve gear that was revolutionary for its time.
But physical danger was only part of the hazard. Call boys worked around the clock with no set schedule. They slept in rail yard shacks between calls, eating whatever the cook car provided.
Today, a group of enthusiasts is building a brand new P2 from scratch, attempting to recreate what Thompson destroyed. It is the ultimate tribute to a locomotive so rare that none survived. Number 13, Pennsylvania Railroad Q1.
Sleep deprivation was constant. Many developed lifelong health problems from years of irregular hours during crucial developmental years. The position existed because railroads refused to install telephones in workers' homes.
In 1942, the Pennsylvania Railroad built exactly one Q1 locomotive, and it was unlike anything else on rails. This 4644 duplex drive monster was an experimental testbed for ideas that would later appear in the famous T1 class. But the Q1 was stranger than any of them. The wheel arrangement alone was bizarre, with a 4-wheel leading truck, 6 driving wheels in one group, then another 4 drivers in a second group, followed by a 4-wheel trailing truck.
That would cost money. A call boy cost almost nothing. By the 1920s, most railroads finally equipped crew dispatch offices with telephone directories.
But here's what made the Q1 truly experimental. It served as a rolling laboratory, testing everything from streamlined shrouding to advanced valve gear. Lessons learned from the Q1 directly influenced the 52 T1 locomotives that followed. After just 4 years of service, the Q1 was scrapped in 1946. Only one was ever built. Only one was ever needed.
The cars weren't secured, and they could start moving at any moment if a switchman coupled another car to the string, or if a hump yard sent cars rolling downhill. Death came quickly, and without warning. One Pennsylvania Railroad report from 1897 noted that car knockers suffered casualty rates triple those of other yard workers. The problem was time pressure. Yards processed hundreds of cars daily. Inspectors had minutes to examine each one. Rushed inspections meant missed defects, and missed defects meant derailments down the line. But slow inspections meant trains leaving late, and late trains cost money. Management always chose speed over safety.
These locomotives could do things no British passenger engine had done before. They regularly handled trains that would have required double heading with any other power. But here is the tragedy. After Gresley's death, his successor Edward Thompson rebuilt all 6 P2 locomotives into conventional Pacific types, destroying their unique 282 wheel arrangement forever. Every original P2 was gone by 1944. Building custom steam locomotives in tiny quantities could not compete with mass-produced diesels. The 2 Class 10 locomotives served faithfully until 1967, outlasting diesels that were supposed to replace them. When they were finally retired, both were preserved, a recognition that these were not just locomotives, but monuments to an era.
Exposure during sudden storms. The track walker vanished. Some were found weeks later. Others never were. Then the railroad hired a replacement. Number 14. Car knocker. The name alone tells you how rough this job was. Car knockers inspected freight cars by literally hitting them with hammers, listening for cracks in wheels and frames. A skilled car knocker could identify a fractured axle by sound alone. A distracted one ended up under the next train. These inspectors worked in busy yards where cars rolled constantly. Their job required crawling beneath loaded freight cars to check brake rigging and running gear. But the real danger came from the trains themselves. Track walkers worked on active lines. They had to time their inspections between scheduled trains, stepping aside at the last moment. Years of close exposure to passing locomotives destroyed their hearing, which made the job even more dangerous.
These were not ordinary engines. They featured streamlined shrouds, roller bearings throughout, and welded boilers that represented the absolute pinnacle of German steam technology. Each produced 2,500 horsepower and could sustain speeds over 160 kilometers per hour with heavy express trains. The Class 10 locomotives were designed to compete directly with diesel locomotives, and on performance alone they succeeded. But economics told a different story.
Railroads ran on information as much as steam. Telegraph lines ran alongside every track, carrying train orders that prevented collisions.
Oliver Bulleid was either a genius or a madman, and the leader class supports both arguments equally. In 1949, the Southern Railway unveiled a locomotive that looked nothing like anything built before. It was fully enclosed, double-ended, and designed to operate in either direction without turning.
The fall rarely killed instantly. Instead, workers lay with broken backs beside remote tracks, waiting for help that might never come. Yet dispatchers demanded immediate repairs regardless of weather. A dead telegraph line might cause a head-on collision. A dead lineman merely required paperwork. The job vanished as telephone networks replaced telegraph systems.
It looked like two locomotives had been welded together. The Q1 weighed over 600,000 pounds and could generate 76,000 pounds of tractive effort, making it one of the most powerful passenger locomotives ever built. The engine's massive size created immediate problems. It could not negotiate the curves on many Pennsylvania railroad lines, limiting where it could actually operate. The complex duplex drive mechanism required specialized maintenance that most shop crews had never encountered.
Railroad bridges had to be built fast and cheap. That philosophy killed bridge workers by the hundreds. Timber trestles went up in weeks, often before the wood properly dried. Iron and steel bridges required workers to balance on narrow beams 100 feet above raging rivers with no safety equipment whatsoever. Falls were constant. One Union Pacific construction report casually mentions losing 4 men during a single bridge project, as though discussing misplaced tools. The bodies were rarely recovered from canyon floors or river currents. Funerals happened without corpses, but falling was only one hazard.
Locomotive number 05002 achieved something extraordinary. It reached 200.4 kilometers per hour, roughly 124 miles per hour, becoming the fastest steam locomotive in the world at that time. The record stood for years. These were not just fast in a straight line. The Class 05 locomotives regularly hauled elite express trains at sustained speeds that made other railways look primitive.
The most dangerous bridges crossed active rail lines. Construction happened between trains, with workers scrambling clear when locomotives approached. Timing errors proved fatal regularly. One Pennsylvania Railroad bridge project recorded 9 deaths during construction, 7 from falls and 2 from being struck by trains. Number 10. Hostler. The hostler moved locomotives around roundhouses and service facilities. It sounded like the safest job in railroading. After all, hostlers just repositioned engines at slow speeds within yard limits. What could go wrong? Everything, apparently. They squeezed between locomotives separated by inches. They operated engines while mechanics worked underneath, trusting hand signals in noisy, smoke-filled buildings. Boiler explosions killed hostlers regularly.
3 built, 1 survivor, and a world record that proved steam power had not finished evolving. Before the Virginian tried and failed, the Erie Railroad attempted something even more ambitious. Their streamlined shrouds, designed by German aerodynamicists, reduced air resistance to levels previously thought impossible for steam power. But the war changed everything. The streamlined shrouds were removed to simplify maintenance. In the 1930s, Nazi Germany was obsessed with speed and records, and that obsession produced 3 of the most remarkable steam locomotives ever built. The Class 05 engines were streamlined 464, Hudsons designed specifically to break world records. Only 3 were ever constructed. On May 11, 1936, the Leader proved you could disguise a steam locomotive as something else, but you could not make it work like something else. It remains the most radical British steam locomotive ever attempted. Number 9, DRG Class 05. The crew sat in a cab that could have belonged to a diesel. The entire running gear was hidden inside a metal shell. Only 5 leaders were started, and just 1 ever turned a wheel under steam. The problems were catastrophic. The enclosed design trapped heat so severely that temperatures inside the engine room exceeded 140 degrees Fahrenheit. Crew members risked heat stroke just doing their jobs. The chain drive to the wheels created a racket and communication was impossible. But the Leader's biggest problem was timing. By 1950, British railways had committed to dieselization. Nobody wanted an unconventional steam locomotive, no matter how innovative. The single operational Leader made a handful of test runs before the program was canceled. All 5 were scrapped before any entered regular service.
Steam and boiling water created another constant threat. Roundhouse locomotives sat with boilers pressurized, ready for service. Leaking valves scalded workers without warning. Number 9. Flagman. When a train stopped unexpectedly, someone had to walk back along the track with flags and flares to warn approaching trains. That someone was the rear brakeman, serving double duty as flagman. Trains killed them when they wandered onto adjacent tracks without realizing another train approached from the opposite direction. The isolation was brutal. Flagmen stood alone in wilderness with only a kerosene lantern. The job meant walking alone into darkness, often in terrible weather, knowing that a second train might appear at any moment. Flagmen positioned themselves far enough behind the stopped train to give approaching engineers time to brake.
Between 1914 and 1916, the American Locomotive Company built 3 massive triplex locomotives for the Erie Railroad's mountain grades. These two 8882 behemoths featured the same 3-engine concept as the later Virginian machine, but with an even more complex arrangement. The tender itself was powered with one set of driving wheels beneath the coal and water supply. On paper, the Erie Triplex looked revolutionary. 3 connected engine units would provide 160,000 pounds of tractive effort, enough to move mountains. The Erie needed exactly that kind of power for the steep grades through New York's southern tier. Reality was less cooperative. Like all triplex designs, the single boiler could not keep pace with the steam demands of 3 engine sets at anything above a crawl. Crews nicknamed them yard rippers because they excelled at pulling long trains out of terminals but could not maintain speed on the main line. The traction beneath the tender created problems, as the engine units fought each other rather than worked together. All 3 Erie triplexes were eventually rebuilt into more conventional configurations. The triplex concept died on those grades, a bold idea that simply could not overcome the physics of steam generation. The system could recover up to 90% of the water used, extending range to nearly 500 miles between stops. Only 90 Class 25 condensing locomotives were ever built. The complexity was staggering. 6 steam-driven fans forced air through miles of radiator tubing while the locomotive thundered across the desert. Maintenance crews battled scale buildup and tube failures constantly.
Steam locomotive boilers accumulated scale and sediment that reduced efficiency and caused dangerous hotspots. Removing this buildup required men to climb inside the boiler itself. Boiler washers crawled into metal containers barely large enough to hold a human body, scraping mineral deposits in near-total darkness while scalding water dripped from surfaces that might still hold residual heat. The confined space could kill in many ways. They swung sledgehammers to drive spikes. They lifted rail segments weighing hundreds of pounds. They tamped ballast until their arms went numb.
Number 6. LNER W1 Hush Hush. In 1929, the London and North Eastern Railway unveiled a locomotive so secret that even its own workers called it Hush Hush. The W1 was Britain's only high-pressure locomotive, featuring a water tube boiler operating at pressures that would have been familiar on a warship but were unheard of on rails. Conventional locomotive boilers operated at around 200 pounds per square inch. The W1's marine-type boiler ran at 450 pounds per square inch, more than double the normal pressure. Only one was ever built, numbered 10,000, and it looked unlike anything else in Britain. The streamlined casing hid a boiler so experimental that even its designers were not entirely sure what would happen. In 1944, the Pennsylvania Railroad unveiled a locomotive that sounded like the future. The S2 was powered not by pistons, but by a steam turbine connected directly to the driving wheels. No rods, no reciprocating motion, just smooth turbine power spinning the drivers at speeds up to 100 miles per hour. Only one was ever built. The S2 measured 123 feet long and produced 6,900 horsepower, making it one of the most powerful steam locomotives ever constructed. It was a coal-burning locomotive with diesel-electric running gear. Only 3 were ever built, and their problems began immediately. Coal dust and ash were the enemies of precision machinery. The turbine blades accumulated deposits that threw them out of balance. The generators ran hot. The traction motors struggled under load. Maintenance logs from the era read like horror stories, with crews fighting endless battles against fouled components and overheating systems. At speed, the ride was eerily smooth. No hammer blow from reciprocating rods meant less track damage and a quieter cab. The turbine whispered while conventional locomotives pounded. But the S2's fatal flaw was economics. Turbines operate efficiently at high sustained speeds. Real-world railroading involves constant acceleration, deceleration, stops, and starts. At low speeds, the S2's fuel consumption was catastrophic, burning coal at rates that made dispatchers wince.
Every locomotive on this list failed for specific reasons: bad weight distribution, inadequate boilers, complex controls, turbine inefficiency at low speeds. But their collective failure tells a larger story about engineering hubris meeting economic reality. The 1940s experiments weren't stupid. Many incorporated genuinely brilliant innovations that would later appear in successful diesel and electric locomotives. Electric traction motors, automatic controls, streamlined car bodies. The engineers weren't fools. They were desperate. Diesel locomotives offered something steam never could: turnkey simplicity. A diesel started with the push of a button. It required no fire building, no water treatment, no ash disposal. 2 men could operate what steam needed 5. Maintenance intervals stretched from days to weeks. Fuel efficiency remained constant regardless of speed. Steam's fundamental problem wasn't technology, it was thermodynamics. Even perfect steam locomotives waste 70% of fuel energy as heat. Diesels waste only 30%. No engineering could overcome that basic physics. These 20 locomotives weren't just failures. They were steam's death throes. Each proved the future belonged to internal combustion. And that's all, folks. These 20 locomotives represent steam's final desperate gamble against inevitable diesel domination. Don't forget to subscribe for more tales of engineering ambition meeting mechanical reality. Here's another video I've specially selected for you. See you next time.